last section of Chapter 7, which is talking about the idea of expected value. So as we kind of start this unit, we're going to be able, or this section, we're going to be able to calculate the expected value, interpret it, and then use it to analyze applications or use it to make future predictions. Okay, expected value sounds a lot kind of crazier and more intense than it is. The expected value is the mean of the outcomes. Okay, essentially expected value is what you would expect to happen in a series of trials over time. So what I mean by that is, let's refer to gambling, right? In gambling, the house always wins, eventually over time, right? You could have a great night at the casino and you could walk out of there with $1,200. Eventually, though, the house is always going to win. And the reason that we say that is because it comes from the expected value. And so it's the mean of all the outcomes. So even though there was a night that you walked out with $1,200, there was also somebody else that walked out and they lost $300. There was another person that walked out, maybe they lost $2,000. Bad night for them. But so it's the mean of every possible outcome as it trends over time. All right, so speaking of casinos. In the casino game Keno, a machine chooses at random 20 numbers between 1 and 80 inclusive without replacement. Players try to predict which numbers will be chosen. Players don't try to guess all 20, though. In general, they'll try to predict 1 and 10 of the chosen numbers. The amount 1 depends on the number of guesses they made and the number of guesses they made and the number of guesses that were correct. So if we think about this, okay, just talking about it in terms of expected value, the way that we would kind of set up our expected value, okay, would be kind of what are all the possible outcomes. Okay, so if they're guessing between 1 and 10 numbers, okay, then they're guessing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total numbers. So one of the probabilities would be that they get all 10 right. And we're not going to go through this whole example because I've got other ones coming up. Another probability is that they get 9 out of the 10 right, 8 out of the 10 right, 7 out of the 10 right, and so on and so forth. So these are the outcomes. And then what we also want to look at is what the probabilities of those outcomes are. Okay? So as you can imagine, getting all 10 right would be pretty impossible. So this is probably going to be a pretty low number, so close to 0. Not impossible, you can definitely guess all 10 right. But then you can see too, as we get down to where you might be guessing 1 out of the 10 right, still probably not going to be an amazing probability since you're picking from 80 numbers, but it's going to be definitely greater than the first probability. All right, so that's, and I know this doesn't make a ton of sense yet because we're just trying to talk about kind of the setup of these. But so when you're looking at these, what you want to think about is how likely is one of these events occurring. So 10 out of 10, probably not very likely. But guessing 1 out of 10 numbers, again, probably still not crazy likely because you are picking out of 80 total numbers, but it's definitely going to be more likely than getting all 10 right. All right, so this is a different setup. So this one says you pay $2 to spin a spinner. On the spinner, there are 6 green wedges, 4 red wedges, and 2 blue wedges. If it lands on green, you lose. If it lands on red, you'll be given $5. If it lands on blue, you'll be given $8. So let's think about the outcomes here. And I'm going to orient this one horizontally this time rather than vertically. All right, so you pay $2 to play the game. All right, if it lands on green, you lose. Well, I guess I could even color code this, couldn't I? All right, so that is one outcome. You lose $2. That's a bummer. The next outcome you have is if it lands on red, you'll be given $5. Now, something to keep in mind here is that you paid $2 to spin this spinner, okay? So even if you're handed $5 back, your net, okay, what you actually earned was only $3. Okay, so another way to think about this, I'm just going to use an example from my life, okay, is like 50-50 tickets at like ball games and stuff. Okay, so last night my little brother had a baseball game. We went, we did the 50-50 tickets, and so we did 7 tickets for $5. Okay, so if one of our tickets had won, and the pot last night was $80, I think, okay, technically I only netted $75, right? Because I paid $5 to buy those tickets. And then I was given 80, but again, we have to think about what did I actually net? I really only netted $75. If I were to win, I didn't. All right, so same thing with blue, right? If it lands on blue, you'll be given $8. So again, you're really netting 6. All right, so the next part of this is what are the probabilities of these events? All right, so going back to green, there are 12 total wedges on our spinner. 6 plus 4 plus 2 gives us 12. Of those, 6 are green. Okay, so probability you land on green would be 6 out of 12. Of course, you can reduce that to 1/2. Then, if it lands on red, so that's 4 red wedges, so 4 out of 12. And then lastly, if it lands on blue, so that would be 2 out of 12. So then to actually finally do the math to calculate the expected value, we're going to multiply the outcomes times their probability and add those together. And I'm going to abbreviate expected value to EV. So green, we have -2 times 6 out of 12. And then we would add that to the red probability. And lastly, we add that to the blue probability. And then we're going to take that information and figure out what the expected value is in Desmos. So again, first outcome was -2 times 6 out of 12. Our next outcome was 3 times 4 out of 12. And finally, 6 times 2 out of 12. Okay, so we get an expected value of 1. So over time, what that expected value of 1 means is that if you were to play this game over and over and over and over and over and over again, okay, that actually over time, your expected value is going to be to earn $1 off this game, right? So this game is actually in favor of the player rather than in favor of the house, which we don't see a ton, but this is a very nice spinner apparently. So again, this is not saying every time you go up there you'll get $1. We can see there's no outcome that's $1. But it's saying as you play this game over time, let's say you play 1,000,000 times, we would expect you to overall earn an average of $1 on each game. All right, take a look at the next one. As the CEO of a company, you're deciding if you want to invest in a new project. It will cost the company $35,000 to invest. There's a 25% chance you will lose $200,000 on the project. There's a 35% chance you'll break even, and there's a 40% chance you will earn $125,000 should you invest. Okay, so when we go to set up this problem, again, we want to look at our possible outcomes. I'm going to color code them again. Okay, so one of the outcomes is that you're going to lose $200,000, and that's probably in addition to the $35,000 you spent to invest. Not great. So one of those outcomes would be losing $235,000. Good. Not ideal. Another outcome would be that you will break even. Now, when we say break even, what that means is even though you paid the $35,000 to invest, your company earns the $35,000 back, and now zero. So you did the project, you netted zero, that's where you're at. And then lastly, 40% chance you'll earn $125,000. Okay, again though, you invested $35,000, so really your company is earning $90,000. All right, so looking then at the probabilities. So there's a 25% chance that life is not great. And I'm going to convert that to a decimal, so 0.25. Then you have got a 35% chance you're going to break even. And lastly, 40% chance you're going to earn that $90,000. And so very similar to the last one, we're going to multiply the probabilities and the outcomes together and then sum those up. And now we'll calculate this out in decimals. So we can see here that our expected value would be negative $22,750. So if I'm looking at this from a CEO's point of view, right, that's a negative expected value. So over time, as if we were to think about this project over and over, my company would be losing on average about negative $23,000 every time we invested in this opportunity. So to me, no, absolutely not. I don't think that that's a great idea. Now, something I'm just going to pop in here and add an extra slide to talk about one other thing. And it's something that I mentioned a little bit earlier, as far as the house versus, the house versus like the player. Okay. So when we look at expected values, you can have kind of basically three things happen. You can have a negative number, you can have it be zero, and you can also have it be positive. Okay, so as we take a look at those ideas, what we want to think about is how it relates to basically like who's winning, who's earning it. So if you get an expected value that's negative, this game is bad for the player, good for the house, if you will. Okay, so that means that over time, the player is going to lose money. They're going to, or whatever it is that they're using. They're going to basically end up with a negative expected value, but that means that the house is earning more money. If you get an expected value of zero, which is typically what you are going for, this is what we call a fair game. So what that means is it is not tipped in favor of the house nor the player. It is a fair game. If you think back to one of the examples we did in one of the last sections that talked about Anna and Ben flipping the coin, because they both had an equal probability of winning, that would be a fair game. And then lastly, you have if it's positive, and that means that it's good for the player, bad for the house. So, ideally that's the type of game me as a player I want to play. If there's a blackjack table that for some reason is giving out expected values that are positive, put me on that table. But a lot of times what will happen with games like these, where they are in favor of the player, is they'll get reset, they'll figure out what's going on. A lot of time, I'm referring more to like casinos, that type of thing. But even like carnival games, if you think about like the games that you can play at the fair, if overall, more and more people are somehow, knocking over all the bottles or, winning the little duck water shooting competition, they're going to figure out what's going on and why the house is losing money. All right, so this is it for 11, or I'm sorry, for 7-11. And for chapter 7, I will see you next time.